Connecting power with incorrect polarity is an easy mistake that can blow out your device. Bad things can happen when you reverse the polarity of your device's power supply. Swapping the positive and negative power leads is probably the primary method of damaging your new circuit board or PCB. Reverse polarity can also occur after the testing and development phase. A device will generally be designed so as to prevent the end user from incorrectly plugging in a power cable, but even the best of us might occasionally insert a battery without looking at the polarity diagram. I prefer to use whatever means are available to make reverse polarity physically impossible, but the bottom line is that the device is never truly safe unless the circuit itself is able to survive a reversed supply voltage. In this video, we'll examine two simple yet highly effective ways to make your circuit strong against power supply polarity catastrophes. What is a reverse polarity protection diode? You can, in fact, acquire reverse polarity protection using a diode. Yes, all you need is one diode. The idea here is to put the diode in series with the supply line. If you're not familiar with this technique, it might initially seem a bit strange. Can a diode change the polarity of an applied voltage? Can it really isolate the circuit from the applied voltage? It certainly cannot undo the reverse polarity, but it can isolate the rest of the circuit from this condition simply because it will not conduct current when the cathode voltage is higher than the anode voltage. Thus, in a reverse polarity situation, damaging reverse currents cannot flow and the voltage across the load is not the same as the reversed power supply voltage because the diode functions like an open circuit. Reverse polarity protection using a diode. The easiest way to provide a reverse polarity protection to a circuit is by connecting a diode in series. A reverse bias diode does not allow a current to flow through it, and thus the attached circuit is unpowered if a reverse voltage is applied and won't be damaged. This circuit is probably the most common reverse polarity protection circuit and used in many products. One example for this is the Arduino Uno's barrel jack connector. As shown here, there is a diode right next to the connector to protect the Arduino from an accidentally applied reverse voltage. Note that this protection only applies to the barrel jack. If you directly apply the reverse voltage to the VIN pin, you can still destroy your Arduino Uno. The use of a reverse polarity protection diode in series to a circuit impresses by its simplicity and the fact that no current flows if a reverse voltage is applied. There are some drawbacks regarding this solution, however. The voltage drop over the diode is around 0.7 volts for a normal silicon diode. This is especially an issue with low supply voltage. If you want to power 3.3 volts microcontroller with a lithium polymer battery, you would run into problems if you add a protection diode. Typically, you need a voltage of around 3.5 V if you use a low dropout voltage regulator to create your 3.3 volts supply voltage. A lithium polymer cell reaches a voltage of 4.2 volts when fully charged. With a voltage drop of 0.7 volts over the protection diode, you are already at the minimum operating voltage of 3.5 volts for your voltage regulator, even for a fully charged battery. A Schottky diode is an improvement to this, but the voltage drop is still problematic. In practice, the solution is to just use a polarity-safe connector for the battery. This will effectively prevent reverse voltage without the need for any additional circuitry. If the supply voltage is not an issue, there is still one point to consider: the power dissipation of the diode. As the diode is connected in series, all current has to flow through the diode. In consequence, the diode has to be capable of handling the current consumed by the circuit. Additionally, the diode can cause additional power consumption. Let's look at a different solution that has no negative effect under normal operating conditions. A diode can be used as shunt. A shunt is an alternative low-ohmic current path. On this path, the current can pass around the protected circuit in case of reverse polarity. For diodes and LEDs, a typical example is the use of an anti-parallel diode. As you can see in the circuit diagram here, the diode is added in the reverse direction of the LED. Under normal conditions, the protection diode is reverse biased and the current flows completely through the LED. In case of a reverse voltage, the diode becomes conductive and limits the reverse voltage over the LED to 0.7 volts. The LED is protected. This method requires that the circuit is not damaged by reverse voltages below the forward voltage of the diode. This is not the case for all components. An example is the ATmega328P microcontroller used on the Arduino Uno, which can only sustain a reverse voltage of 0.5 volts. The use of a Schottky diode should solve this problem in almost all cases, however. The advantage of this solution is that the added diode has no effect in normal operation and still provides protection in a reverse polarity situation. The disadvantage is that there is still current flowing even if a reverse voltage is applied. The diode has to be capable to dissipate enough power. As the diode has a lower voltage drop than the LED, the current is higher in case of a reverse voltage than it would be under normal conditions. In our example circuit, this is not a huge problem, as the resistor is limiting the current. But if a circuit needs a high current, we need a different solution. Here you can see a schematic for a circuit that additionally uses a fuse. If a reverse voltage is applied, the diode becomes conductive and a high current can flow through the diode. Over a long time this would destroy the diode, but if the fuse is correctly dimensioned it blows before this happens. The circuit is now disconnected from the power supply and no current flows anymore. The advantage is that the circuit is powerless once the fuse blows. The disadvantage is that the fuse is irreparably destroyed and needs to be replaced. Additionally, the diode as well as the power supply need to be able to handle the high current that flows until the fuse blows. P-channel MOSFET for reverse voltage protection. The field effect transistor, FET, is a type of transistor that uses an electric field to control the flow of current through it. FET are devices with three terminals that are source, gate, and drain. FET controls the flow of current by the application of a voltage to the gate, which in turn alters the conductivity between the drain and source. This is the basic thing that is used in P-MOSFET as a switch in reverse polarity protection. The P-channel MOSFET is used as a power switch that connects or disconnects the load from the power supply. During the proper connection of the power supply, the MOSFET turns on due to the proper VGS, gate-to-source voltage. But during the reverse polarity situation, the gate-to-source voltage is too low to turn on the MOSFET and disconnects the load from the input power supply. The 100 ohm resistor is the MOSFET gate resistor connected with the Zener diode. The Zener diode protects the gate from overvoltage. This circuit has all the required components for reverse polarity protection. The V1 is the source that is in perfect polarity. The P-channel MOSFET is getting biased from the resistor 100 ohm and the 6.8 volts Zener diode 1N4099. The load is a 10 ohm resistor. The simulation shows the circuit is working properly in the right polarity of the power supply. The Zener diode protects the gate from the overvoltage and the load is getting 1.3 amps with 13.9 volts. It is advisable to use P-channel MOSFET over N-channel MOSFET. This is because P-channel MOSFET is used in the positive rail of the circuit rather than the negative rail. Therefore, PMOS cuts off the positive rails and the circuit will not have any positive voltage. But, N-channel MOSFET is used in negative rails, thus disconnecting the negative rail do not disconnect the circuit from the battery's positive rail. Therefore, in the case of high-voltage DC, disconnecting the positive rail is much safer than disconnecting the negative rail and there are fewer chances of harmful consequences like short circuits. Electrocution will not happen.